Okay, so for the second question of the tutorial day, it's about adjacency matrix, adjacency list, as well as edge list. So this are basically three ways of storing your graph, right? So to recap, adjacency matrix, let's say if I have n vertices, what I'm going to have is I'm going to have an n by n matrix, right, whereby each element is going to state the weight of the edge between the two vertices. So for instance, if my graph is let's say like this, and let's say this points back, right, and let's say the weight of this is 1, the weight of this 2, this 3, then my adjacency matrix is 0, 1, 2, 0, 1, 2. It's going to say that 0 points towards 1 with a weight of 1, 1 points to 2 with a weight of 2, and 2 points to 0 with a weight of 3, and everything else is 0. Right? This is for a directed graph, right? Some pointers to note, if it's unweighted, then all this would just be 1. If it's an undirected graph, then the graph will actually be symmetrical, right? Because if 0 is pointing to 1, then 1 will also be pointing to 0, and so on. Right, so this is adjacency matrix. So the amount of space that we need to store this is OV squared, right? Because where V is the number of vertices, because it's V by V matrix. And now we go to adjacency list. So for the same graph here, right? For the same graph here, what adjacency list is going to do is 0, 1, 2, right? Instead of storing this entire line, what it's going to store is going to store a pair, right? It's going to say that it is connected to 1 with a weight of 1. 1 is connected to 2 with a weight of 2, and 2 is connected to 0 with a weight of 3. Right, and this is my adjacency list. Right, notice here that in this case, we actually need only OE amount of space, right? Because if 0 is not connected to something, it wouldn't be here, rather. So instead of storing zeros, we actually save that amount of space. So the amount of space we need is only OE. And finally, we have edge list. So in this case, edge list is going to store, as the name suggests, a list of edges. So what it's going to store is it's going to say 0 is connected to 1 with a weight of 1, right? Followed by 1 is connected to 2 with a weight of 2. And finally, it's going to say that 2 is connected to 0 with a weight of 3, right? So edge list, adjacency matrix, and adjacency list, right? So which one you want to do, which type of way you want to store your graph depends on what application you want to use. So usually, let's say if you want to do a lot of neighbor queries, then edge list would not really make sense, because it's very difficult to find out, let's say from a list of edges, whether 0 is connected to, let's say, 2, right? Because you actually have to run through each edge to check whether 0 is connected to 2, and that runs in OE amount of time, right? On the other hand, if you use adjacency matrix, right, you're just going to take a O1 to basically check, okay, 0 is connected to 1 and the weight is 1, right? So this is, you can check neighbors in O1. And adjacency list is still better than adjacency edge, because edge list, because instead of checking through all the edges, you just need to check the neighbors of 0. So let's say if I want to find out whether 0 is connected to 2, I just need to check the list corresponding to the index 0, which is much less than OE, usually, right? Of course, in the worst case scenario, it could still be quite large. Yeah, but of course, the trade-off here is that the adjacency matrix, you need much more space to store. So you need OV squared amount of space to store. Sometimes if you only need to keep iterating through edges, which we'll see in the future when we do minimum spanning trees. So sometimes you want to only iterate through edges, then edge list may make sense. Another thing about adjacency matrix is that if you square the matrix, you actually get whether two, let's say if this is 0, 1, 2, right? If I square the matrix, right? So n by n matrix times n by n matrix, you still get back n by n matrix, right? So the value here is going to correspond to, say, it's going to, what it's going to mean is 0 connected to 1 in 2 hops, right? So if this value is not 0, then 0 is connected to 1 in 2 hops, and that's because we square it. And similarly, if we cube it, it's going to say it's 0 connected to 1 in 3 hops, and so on. So that's one extra thing that adjacency matrix can do that these other two ways of storing your graph does not.